Good morning, everybody. Welcome back. So we're going to finish up our discussion of Chapter 6 today. And here is where we've gotten to so far. So far, what we've done is we've defined the energy of a single particle, which is gamma mc squared, and realized that it could be divided into two components: its rest energy, which is the energy it has just by virtue of having a non-zero mass, and its kinetic energy, the energy it has due to any motion. And we've also found that if something's going near the speed of light, then you have to get kinetic energy by subtracting mc squared from gamma mc squared. But if its speed is much lower than the speed of light, then its kinetic energy is approximately half mv squared. Last time we looked at the energy of multi-particle systems, and we discovered that in addition to kinetic energy and rest energy terms so if we have a system with three particles, say we'd have particle 1, particle 2, particle 3, there are also interaction energies, which we call potential energy. You can think of it as storing energy. And it's pairwise. So we have the interaction of particles 1 and 2, the interaction of particles 2 and 3, and the interaction of particles 3 and 1. We have been working with, and will continue to work with, the energy principle, which says in its simplest form that the change of energy if a system is equal to inputs from the surroundings, and so far the only kind of input we know about is mechanical work done by the surroundings. And we can write that in an update form also, where final energy in some final state is energy in some initial state plus the work done by the surroundings. And we found that we could calculate potential energy by calculating the work done by objects that were inside the system and then take the negative of that. Now, all of this stuff labeled fundamental is things you need to know. There are results, which will be on an equation sheet, which you don't need to memorize. We got a result that the gravitational potential energy for two interacting objects was minus gmm over r. And that came from what we knew about the gravitational force. The R component of the gravitational force is a minus gmm over r squared. So what are we going to do today? We're going to talk about, the big agenda is just solving energy problems involving potential energy. In order to do that, we're going to talk about some things along the way. We're going to talk about the change of gravitational potential energy near the Earth's surface. We're going to find what the equation for electric potential energy. We'll talk along the way about some general properties of potential energy. For example, the fact that since potential energy, as we can see from this gravitational energy equation here, only depends in a particular state, we can calculate it only depends on the separation of two objects, then the change in gravitational potential energy is independent of how you got from one state to another. It only depends on the initial and the final state, so you could take any path between them. What happens at large distances, talk a little more about the sign of potential energy, and work a little more with graphs of energy. So that's the agenda for today. Now, so the change in gravitational potential energy near the Earth's surface and for there to be a change in gravitational potential energy, it must mean that we've chosen a system which is Earth plus something. So the Earth is now internal to our system. And we know that if we just chose something like a falling ball or something, we could calculate the work done by the Earth It's just the gravitational force near the Earth's surface times the displacement, taking care of the sign, whether the directions of the force in the displacement are the same or opposite. And we'd get an mg delta y. But what we have for gravitational potential energy is the general form. The change of gravitational potential energy is would be a minus g. It's u final minus u initial. And so that would be a minus gm over the radius of the Earth plus delta y, which could be positive or negative, right? Minus a minus gmm over the radius of the Earth. So how do we get a simple form for that? Well, we note that delta y is going to be really, really small compared to the radius of the Earth first. But if we do some algebra and just get a common denominator by multiplying this side by radius of the Earth plus delta y over radius of the Earth plus delta y, and this by RE over RE, we can just simplify this, do some algebra and simplify it. And what we get is a minus g mass of the Earth, mass of the object, times a negative delta y over the radius of the Earth squared plus the radius of the Earth times delta y. And this term here is going to be a lot smaller than the radius of the Earth squared, so we can neglect that and say that this is approximately equal to, let's see, these minus signs actually cancel, so we have a gm over the radius of the Earth squared times an m delta y. Well, this term is just our friend little g, the magnitude of the Earth's gravitational field near the Earth's surface. And so this ends up being approximately equal to just a plus mg delta y. So does that mean that we saw a graph of energy, of the gravitational potential energy as a function of distance that looked like this, and it was a negative quantity? Does that mean that potential energy is actually negative near the Earth's surface? And the answer is actually positive. I mean, but this is a positive number, so how is that possible? Well, notice that what this is equal to is not potential energy, it's equal to a change in gravitational potential energy. So it's actually, the change can be positive, even though, so we could be going from here to here. The change could be positive, even though the quantity is negative. And in fact, we can actually write the gravitational potential energy near the Earth's surface as this. We can write it as the gravitational potential energy at the surface, plus this extra term, mgy, where y is the distance above the surface. Now this is a negative, and this is a negative number because this is a very large negative number, and that's going to be a small positive number. So really we're writing the change in gravitational potential energy is equal to near the Earth's surface as equal to minus g mass of the Earth, mass of the object, over radius of the Earth plus mgy final minus g mass of the Earth, m over radius of the Earth, plus an mgy initial. And these two things cancel, and we're left with this mg delta y expression. So that's convenient, so we don't have to use that full formalism when we're near the surface of the Earth. So let's talk about solving some problems using potential energy. Energy problems are really simple to solve because you always do them exactly the same way. No matter what you're trying to solve for, you always do it exactly the same way. So if you do it systematically this way, you'll always be able to solve the problem. So the first step is to choose a system. And we'll often find that in cases where we can calculate potential energy, it's very much simpler to choose everything as the system. And we'll see why in a minute. Then we have to write out the energy principle. I happen to like the form E final is E initial plus work by the surroundings. Then we have to expand out the terms. So we have to take E final and write all the pieces of it. So there might be some K's and some U's and some MC squareds. And there might be some K's and U's and MC squareds. Okay, here. But if we've chosen everything as the system, then the work by the surroundings is zero because there's nothing in the surroundings to do work, so there's no input. And then all we're left to do is to, in our expanded terms, we find our unknown, which may be hiding here or there or whatever. So find the unknown. Where's Waldo? And then solve. So that's actually all there is to it. The key, some pieces that you have to be systematic are about our choose system and initial and final states. So this actually takes some thought. This takes wrapping your head around the problem to figure out what the initial and final states are, because we have a final state and initial state. What are they? What do they mean? And expanding the terms, you have to be careful to think about both the system and the initial and final states. Okay, so you don't put terms in there that don't belong there, and you don't leave out terms that are necessary. That's really sort of the key issue here. So let's solve a problem that's actually a little bit familiar to you, because or let's talk about solving a problem that that's a little familiar because you actually did this computationally at one point. So let's talk about finding escape. I really can spell escape speed. What's escape speed? Well, as you know, the escape speed is the speed an object would need to be able to get infinitely far away from something like the Earth, even if it's barely moving when it's super far away. So the idea is, and you did this with the spacecraft and the Earth, right? Except you didn't wait infinitely long to see, and you did it by trial and error to see what speed you need to give a spacecraft that was moving directly away from the Earth so it could get super far away, slowing down, speed approaching zero. But so we choose a system, and that would be the spacecraft and the Earth. And initial and final states, it's helpful to make a diagram. So here's the Earth, here is the spacecraft, here's its initial velocity. So this is the initial state. The final state, here's the Earth, here's the spacecraft. Actually, essentially at rest, and this distance is infinity. And when it gets infinitely far away, it's at rest. So that's the definition of escape speed. That's the final state. So, so now we would write the energy principle. So this is one, and now two, write the energy principle. The final energy is the initial energy plus work done by the surroundings. And now we have to expand this. So we have two objects, so we need to include both of them. So the final energy of the spacecraft, I guess I should write kinetic energy of the spacecraft plus the kinetic energy of the Earth plus the rest energy of the spacecraft plus the rest energy of the Earth plus the final gravitational potential energy of the interaction, because there's still two objects in our system, is equal to the initial kinetic energy of the spacecraft plus the initial kinetic energy of the Earth plus the rest energy of the spacecraft plus the rest energy of the Earth plus the initial gravitational potential energy plus zero, because since there's nothing in the surroundings, that we know that term is zero. Now, the next thing to do is to simplify this. And we were really compulsive here, so we put in everything. We know the rest energy of the Earth isn't changing because it's not turning into solid gold or something. So we can cancel that from both sides. And we know the spacecraft's rest energy isn't changing. And in fact, we might have decided not to put those in this equation, and that would have been okay because we were already making a judgment that there was no change of identity here. It's also probably the case that the change in the Earth's kinetic energy is really negligible. The spacecraft does exert a force on the Earth. It's pulling on the Earth, but the Earth is very massive. And so the change in its speed is tiny. And so we can say that the change in Earth's kinetic energy is zero, and the final kinetic energy is roughly equal to the initial kinetic energy. And now we just have to take one more step in writing out these terms. So we have a half mass of the craft, final speed of the craft, plus minus g mass of the Earth, mass of the spacecraft, divided by infinity in this case. And physicists are very happy writing 1 over infinity is equal to 0. Your math teacher might not like that, but if it makes you uncomfortable, then you can stick you can write it as the limit as r goes to infinity of 1 over r is 0. But for shorthand, we just write 1 over infinity is equal to 0. Is equal to the initial kinetic energy, so a half mass of the craft, the initial squared, plus the initial gravitational potential energy, and the initial distance was the radius of the Earth plus a few 40 or 50 kilometers, so not a big deal, basically. And a potential energy. Now notice here, before we go any further, that this is an interesting equation because the mass of the spacecraft appears in the numerator of each term. So actually, we could divide through by that. It cancels out, so that this is true for any value of the mass of the spacecraft or a rock or whatever. Anything trying to escape from the Earth would actually have to have the same initial speed to do that. And now we can go a little further, because given the definition of escape speed, what is that? What is V final? Right. Yep, V final is 0. So that's 0. And now we're left with an equation that we can solve. So where's our unknown? Well, the escape speed, now we have to think about the problem. The escape speed is the initial speed the object needs to get away, right? So therefore, this is our unknown. And if we know the mass of the Earth and g and the radius of the Earth, we can now solve this to get the escape speed. So we can which you found empirically to be something like 10 to the 4th meters per second, I think, roughly. But now we could predict it exactly. So this is kind of a template for every energy problem we're going to do. The algebra isn't hard. What's important is choosing a system, being careful about the initial and final states. That's where understanding the problem matters. Expanding writing out, starting from the energy principle, writing out all the terms, and then deciding which ones are 0 and which ones don't change, and then finding the unknown. And that's essentially, and it doesn't matter if there's a change of identity or anything else, you do it exactly the same way. Right, so that's an interesting point. So the question is, the potential energy would go to 0. And that is a feature of these potential energy equations, so that if we have, this is energy versus separation. We know that the gravitational potential energy, if we look at this equation, when r is a very large number, when r is infinity, then that comes out to 0. So it basically approaches 0 here. And as r gets small, this term gets bigger, but it's large and negative, so it actually goes to negative infinity, essentially, as if you got infinitely close, which of course you can't do to a star or a planet. In fact, if this is our spacecraft Earth system, so this would be U gravitational. If this is the spacecraft Earth system, there's some value here, the radius of the Earth, beyond which it doesn't make sense to plot this curve because the spacecraft has crashed on the Earth. Okay, so you can't actually get to this region. So for any real system, it's going to be something like that. Okay, so let's actually look at how this plays out in some orbits and some other situations like that. So I'm going to switch to GlowScript here. And so here's a program where some object orbits planet, say. And we're going to ask it to make a graph as we go. We're going to plot energy as a function of separation, but we're going to plot not only, so at every, what the loop looks like in this program is that calculate the gravitational force and update momentum, okay, just like you did in your orbit program. But then, after doing that, since you know the momentum and you know R because you've already calculated, you can calculate the kinetic energy of this spacecraft and the gravitational potential energy of the Earth craft system. And here we're assuming that the kinetic energy of the Earth doesn't change, so we're leaving it out of this. And then we can make a graph, and we can also plot the sum of kinetic and potential energy. So here we've got an elliptical orbit, and the arrow seems to be showing momentum here as the thing goes around. And what are these three curves? Well, the red curve is, so the y-axis is energy, the x-axis is actually separation, not time. That's wrong, that label's wrong. And as a spacecraft or the comet or whatever it is goes around the Earth, we see that as it gets farther away, the gravitational potential energy increases. As it gets closer to the Earth, the gravitational potential energy decreases. And concomitantly, the kinetic, and so here's zero. Note where zero is on this graph. It's up here. Concomitantly, the kinetic energy is smallest when it's farthest away, and it's biggest when it's closest, because in fact it's going slower when it's far away than it is when it's close. And the green line is the sum of this kinetic energy and gravitational potential energy. And that comes out to a number that's, there are two interesting things about it. One is it's a negative number. And two is it doesn't change. Now, why isn't it changing? And we're only plotting it in the range explored by the comet's orbit. So notice that the smallest distance we're plotting here is something like 0.6 times 10 to the 8th meters or something. We're not going all the way to zero, and we're not going farther away than it actually gets. But why is this green line constant? Well, is there anything in the surroundings doing work on this system in our model? Are there any energy inputs to this system? That's right. So there's nothing in the surroundings doing work on this system. It is indeed a closed system. And that means that the energy, the form of the energy in the system can change. It can flow from gravitational potential energy to kinetic energy and back again, but the total amount can't change. And so the sum of kinetic energy plus potential energy actually has to be constant. Now, the fact that it's negative tells us that the kinetic energy never gets big enough for the total kinetic energy is not big enough for it to escape. Okay, so the system is bound. The comet is trapped here. It's bound to the star, and it can't escape because there just isn't enough. It doesn't have enough kinetic energy. So that if the sum of kinetic and potential energy is negative, that gives us a bound system. Now let's try giving it a little more energy by just increasing its initial speed. So let's make its initial speed, let's decrease its initial speed first and see what happens. Okay, so we're going to make it go a little bit slower. Okay, so the sum of kinetic and potential energy is even smaller, and it doesn't get as far away, but we still see this same flow of energy back and forth between. And think about adding the blue curve and the red curve graphically. Okay, so what you would do is take values here and the value here and add them, and you get what you get, right? But clearly, -10 is definitely added to +7 or something is going to give you a -3. It still doesn't. It's still going to be a total negative number. So let's make one more change. Let's give it more energy and see if we can actually get it far away. So I'm just increasing the speed. I'm making it 3.5 times 10 to the third here. And now it looks like it's getting away, but what does the graph tell us? Is the graph telling us this comet is really going to escape? Yep, that's right. K plus U is still negative, so sometime it's going to come back. Now we might have to wait a very long time for this to happen. And now as it gets farther and farther away, these graphs, we see more and more of these graphs, but we know that K plus U is still negative, so we would actually need to add just a little more energy. Let's see what we can do here. Let's make it 3.8 or something. And now the total energy is K plus U is positive, significantly positive, and therefore it's gone. It's never going to come back. So now we have a way based on energy to do what you had to do by trial and error in your program to find an escape speed. So we've explored gravitational potential energy a little bit. Now let's think about electric potential energy. So what we remember about electric forces was that if we have two objects that are positively charged, they exert they repel each other. And if we have two objects that are negatively charged, they also repel each other. And it's only if we have objects with opposite charges that they attract each other. So this is a more interesting situation because electric forces can be repulsive or attractive. Okay, so the situation we've already explored, gravitational potential energy, clearly that's an attractive force and it's only attractive. So things with mass never repel each other. So what we've already seen there is likely to look very similar for this case. But since there can be repulsion, that's actually interesting. Now remember that the electric force was equal to, between two objects that had charges, it was equal to our constant 1 over 4 pi epsilon 0 times the charge of object 1 times the charge of object 2. We had an r squared, and then we had an r hat here. And the way that the direction of the force got captured was by the signs of these two things. It could be positive or negative. And so so algebraically, the sign actually gave us a clue. Now we can follow the same procedure we used. So we can write this as the R component of the electric force is 1 over 4 pi epsilon 0 q1 q2 over r squared. And so if we take the antiderivative, because we know fr is minus the gradient, the derivative with respect to r of u, we get that the electric potential energy is equal to a 1 over 4 pi epsilon 0 q1 q2 over r. Now it still has this 1 over r dependence, but there's some signs here. So it looks like if the signs are the same, it's going to go like 1 over r, and if the signs are different, this thing is going to be negative. So let's see what we can figure out about this. So here's some possible graphs, and let's write our equation here. Electric potential energy was 1 over 4 pi epsilon 0 q1 q2 over r. And so our question is, how many? 4. Which of these graphs would show a graph of the electric potential energy versus the separation for two protons? So the majority said graph 2. We had some votes for everything. So, and the majority is, in fact, correct. It is graph 2. So let's see why it's graph 2. So what we need to do here is think about this equation for electric potential energy. So what we've got here is the electric potential energy is 1 over 4 pi epsilon 0. That's 9 times 10 to the 9th Newton meters squared per Coulomb squared times the charge of a proton, which is 1.6 times 10 to the minus 19 coulombs. There are 2 of those, and then there's some distance. Let's say it's 1 centimeter. So is that going to be a positive number or a negative number? Well, it's going to be positive because everything in this equation is positive. So in this case, it's positive. So that means it can't be 1 and it can't be 4 because it's a positive number. Now, why is it 2 instead of 3? Well, let's think about what happens is when r goes to infinity, we're dividing by a very, the graph has to go to 0, right? So as r goes to infinity, u has to go to 0. And so it can't be that. And when r is very small, then it should be very large and positive. So that's the right. So you need to actually think about the equation. And so this is different from what we've seen because this is a repulsive interaction. So it looks like when 2 things repel each other, the potential energy is actually going to be positive. Think about 2 protons moving toward each other with some initial kinetic energy. As they move toward each other, they're actually exerting forces repelling each other so that they're slowing down, so that the kinetic energy decreases, and that must mean that the potential energy of the system increases because there's nothing around in the surroundings to do work. So which graph would have been if I'd said for 2 interacting electrons? Let's change this question. So now it's electrons. Okay. Which is correct? Which graph correctly represents U for 2 interacting electrons? Okay, so that's better. And you're correct. The majority is correct. So in fact, for 2 interacting electrons, the graph is going to be exactly the same as it is for 2 interacting protons. Because that's still a repulsive interaction. So we have the electric potential energy is 1 over 4 pi epsilon 0 Q1 Q2 over R. This is now a negative number, but this is a negative number also, and so a negative times a negative is a positive, so it still comes out to be a positive number. What about a proton and an electron interacting? Okay, that's a really good question. So let's try that. So we'll make it okay, so now which graph shows the electric potential energy correctly for a proton and an electron. I really urge you to think about the equation here. So put on your algebra hat and think about what happens for different values of separation. So you weren't too sure. The majority said 1, which is indeed correct. Very few people said 2, which is good. But I'm not sure why 3 was popular. I think you're guessing and you're not really looking at the equation. That's what I think you're doing. So let's look at the equation, and you really need to be able to interpret equations here. So the electric potential energy is 1 over 4 pi epsilon 0, Q1, Q2 over R. This is positive, this is negative. So no matter what the value of distance is, what the separation is, what is the sign of this thing going to be? Okay, the sign is going to be negative. And this is an attractive force. So the sign is going to be always negative. So that means we can rule out anything that's positive because that's just not happening. Now, how do you distinguish between 1 and 4? Well, now we actually have to look at the other part of the equation. We have to look at R. And when R goes to infinity, it becomes a very big number. And if you divide by a big number, you get a small number. So the potential energy must go to 0. So U goes to 0 as R goes to infinity. And when R gets very small, it's large but negative. So in fact, okay, so that doesn't have the right properties. So you really need to put on your algebra hat and look at these equations. Have physical meaning. They're not just a thing to plug numbers into. The form of the equation actually tells you a lot about the behavior of the thing you're interested in. Okay, so let me ask you one. So what questions do you have about this? So opposite charges attracting is much like gravitational attraction. Exactly. That's exactly right. And it looks exactly like that. I think you just have to, so why is it negative? It may help you to think about it as bookkeeping. Or it may help you to think about just the properties of potential energy. So it has to go to 0 as objects get infinitely far away, because this is the interaction energy. And as they get infinitely far away, their interaction decreases till it's essentially negligible. So therefore, it must approach 0. As they get closer, think about what's happening to if they're attracting each other, think what's happening to their kinetic energy. Their kinetic energy is increasing, they're speeding up, so it's got to go down. And so it actually has to have these two properties. It must approach 0 as they get far away, and it must decrease as their kinetic energy increases, and that just makes it negative. Think of it as just a bookkeeping thing if you want to. I mean, don't stress out about the fact that it's negative. It's perfectly okay for it to be negative. So Chris, I don't know if your question was the same question. Why is it negative? The axis, this is not exactly the XY plane, because this axis is is energy, and this axis is separation. So it's not it's an abstract thing. It's just energy versus separation. It's not like a spatial. It's not X and Y. Well, the total energy of a system. So the total energy of a system is indeed would for a multi-particle system, it would be K1 plus K2 here plus U12, but don't forget there's an M1 c² and an M2 c², and these quantities are huge. So that this thing always ends up being positive because the rest energy swamps everything. So even if this is negative, kinetic energy, of course, has to be positive. And this is large and positive, so it's always going to come out to a positive number. I suggest that you read this section in the textbook on the mass of a multi-particle system, because it actually, I'm not going to go over it in lecture because we don't have time, but it actually talks about this issue and about the mass of bound systems versus not bound systems, and I think it may make you more comfortable with negative numbers. So now there are various problems we can solve. And I'd like to sketch with you, we may not plug in the numbers, but the solution of a problem that's actually a fairly interesting one. And it has to do with nuclear fusion. And this is one of the processes that goes on in the sun. It's a process that people are still working to try to figure out how to use for power needs on Earth. And it's also the process that occurs in nuclear bombs. And the reaction there's a lot of different fusion reactions. What fusion just means is two things coming together, so different nuclei can react to form other nuclei. But the simplest one, and the one that's sort of one of the primary things going on in stars, is to take hydrogen plus deuterium, which, remember, that's a hydrogen atom that has a proton and a neutron in its nucleus, so it's just heavier. And it makes helium-3 and some energy in the form of photons. So we're talking about nuclei here. When fusion is occurring, it's hot enough that all these things are ionized, so the electrons are not attached to these nuclei. So we're talking about nuclei having to get close enough to react. Now, since the interaction is the strong force, these things basically have to touch to react. So we have to get them close enough to touch, but they don't want to do that, because what we've got is a proton and a neutron, and they're, of course, exerting forces. They're repelling each other. So what we need is to give them very high speeds. We have to give them enough kinetic energy that they have speeds that, even though as they come together, their kinetic energy is decreasing, and they get to the point where they finally actually do touch, so there's a minimum. So let's think about what this graph is going to look like, since we worked on graphs a little bit. So this is two interacting electrons, but it's not two interacting electrons. It's going to be proton plus deuterium. So we have this positive proton and the positive deuterium. Okay? So this is a repulsive interaction. But now you're asking a more complicated question, which is, assuming there's nothing else in the surroundings, so we've got one of each, shooting them at each other. Which of these things is, okay, think about the physics. Okay, so think about which graph is which. Think about what you know about kinetic energy. Think about what you know about potential energy. So break the problem down. First, think about what the potential energy curve looks like. We did a potential energy curve for two interacting protons, right? So what does that look like? So once you've picked the right potential energy curve, then think about what has happening to the kinetic energy as these things get closer together. So Alexander, the photon, remember that photons can have lots of different energies. So visible light is something we detect with our eyes, but there's also lots, and that's an energy of about 1 to 3 electron volts per photon. But there's plenty of other energies that photons can have, and they're just called different things because we can't detect them with our eyes. So infrared photons, which we can detect with our skin and feel as heat, are the same, are just photons. They just have a little bit less energy. They might have about 1/100th of an electron volt energy instead of visible light. Or ultraviolet photons, which are coming from the sun, have about 100 electron volts in energy. So it's nothing's being converted here. It's the photons just coming off the sun just have different an energy spectrum. Okay, you have answered. And okay, all right. So in the end, you did think about it. Good. So this is a repulsive interaction, right? So we know that it can't be 1 because that's a potential energy curve for an attractive interaction. But 2, 3, and 4 are plausible. So indeed, 2, 3, and 4 all have the correct potential energy curve. It's the repulsive one. But 2, in graph 2, we have negative kinetic energy less than 0. Is that possible? So, yeah, no, it's not, is it? How do we get a half mv squared to be negative? We can't. That's always greater than 0. So kinetic energy is always greater than 0. So that's not a possibility. So that leaves the other 2 graphs. And now we're down to, we do want kinetic energy to increase as potential energy decreases. But now we're down to what is the sum of these 2 things? And the question is, how do you add a graph? So let's get rid of that. Okay. And so the way you add graphs is that you take a couple of points and add them together. So we're adding k plus u. So when u is nearly 0, the sum of, so it's good to look at these extrema. When u is nearly 0, the sum of k plus u just has to be equal to k, right? So that sum is going to be there. When k is 0, then the sum of k plus u has to be equal to u. So in fact, that's what the sum actually has to come out to be. So let's just think about this fusion problem and see how we would actually solve it, see how we'd set it up. So we have a proton plus a deuteron goes to a helium nucleus plus a photon. Yep, the answer was 4. So not very many people actually got it right, but there it is. And so what we need to know is, initial kinetic energies. So how much energy we have to give them so they actually get close enough to touch. Okay, so the system is going to be all particles. And there is a change of identity here, so we're going to have to include rest energies, right? And the initial state is far apart. So the initial state is, here's our proton and here's our deuteron, and they're far apart, moving toward each other. And the final state is touching. So they get close enough that they're actually touching. And we're going to say their radii are roughly the same. Okay. So we picked a system, we picked initial and final states. Now let's just write down the energy principle. E final is E initial plus work by the surroundings, and that's going to be 0. And now we need to expand these equations. So initially, we have the kinetic energy of the proton plus the kinetic energy of the deuterium plus the electric potential energy of this system, right? Plus the mass of the proton, the rest energy of the proton, plus the rest energy of the deuterium. And our final state, we have different particles. So we've got the kinetic energy of the helium plus the rest energy of the helium nucleus plus the energy of the photon. And there's nothing else around, so there's no potential energy because these particles don't interact. That a photon isn't charged, it doesn't exert forces on the, okay. But, oh wait, sorry, that's wrong. The final state is not that. The final state was this, so I didn't pay attention to what I said. So the final state really is almost the same. We have the kinetic energy of the final kinetic energy of the proton, the final kinetic energy of the deuterium, the electric potential energy, the mass of the proton, rest energy of the proton, and the rest energy of the deuterium. So I violated a cardinal rule here. I went a step too far and didn't pay attention to what I picked as initial and final states. And now let's think about we're going to have to solve the problem, find out how much energy we get back. We're going to have to use a different final state. But for this, all we're trying to find out is how much energy they need to touch each other. Okay. So in this situation, if we take these initial and final states, The rest energies haven't changed, so we can say those cancel out. And when these things are, so given our final state, these things could be at rest. That would be the minimum energy we'd need to just get them touching and at rest. So in fact, the final kinetic energy and the initial kinetic energy, the final kinetic energy of each thing would be 0. And so again, this is just from interpreting the problem. But there's certainly going to be a potential energy interaction term here. Now, initially, they've got a lot of kinetic energy, but they're really far apart. So what do we know about the initial electric potential energy of this system? We know that it's approximately 0 because far apart. So this equation now reduces to the final electric potential energy of the system is equal to the sum of the initial kinetic energies, which is what we're trying to find, right? Okay, so that's the unknown. Can we calculate this potential energy? Well, we can, actually, because all we need to do is use the radius of the nucleus. So we use radius of a proton is about 1 × 10⁻⁻15 meters. So we would have 1/4πε0. The charge of a proton is 1.6 × 10⁻⁻19 coulombs, and there are 2 of them. Divided by 1 × 10⁻⁻15 meters gives us the sum of the initial kinetic energies. So that's how fast they'd have to go in order to actually touch each other. Now, if we want to find out how much energy we get out, we would have to pick different states. So energy gain, we'd need different states. So we could start with, so our final state would be the helium and the photon moving away from each other. In the initial state, and the energy, and we need to find their kinetic energies. The initial state, we could either pick the state where they're touching, or the state where we have a proton and a deuterium far apart moving towards each other. We could pick either one, and it would work out for us. So again, solving these energy problems is really a matter of just being systematic and writing out the energy principle and applying it.